First of all, I'd like to acknowledge the traditional owners of the land on which we live today and pay my respects to elders past and present, and extend that respect to all Aboriginal and Torres Strait Islander people. I'd also like to acknowledge our guests this evening. We have representatives from the Brisbane City Council, Department of Aboriginal and Torres Strait Islander Partnerships, Ipswich Grammar School. We'll hear more about Ipswich Grammar School a bit later. Queensland Education, Queensland Main Roads, Lend-Lease, and our colleagues from the University of Queensland and Queensland University of Technology, and of course members of the DART family. So welcome to the inaugural Raymond DART lecture as part of the Impact at Griffith Sciences lecture series. And I just want to acknowledge the role of my former Dean of Research, David Lambert. Dave's here, thank you Dave, for setting up the Raymond DART lecture and setting up the series. So we started our Impact at Griffith Sciences lecture series a couple of years ago with the goal of engaging the public and with the diversity of science endeavours that we have at the University, Griffith University. And over the past 2 years we've had a series of lectures that cover a wide range of topics from 3D printing to how automation is going to change our working lives, to climate change and urban planning. And this evening we delve into the world of palaeoanthropology with our special guest, Professor Raymond. Professor Raymond is the head of the Centre for Advanced Study of Human Paleobiology at George Washington University in the US in the Columbian College of Arts and Sciences. And Professor Wood will be exploring our origins. We'll only be exploring the origins of our species, Homo sapiens, but the origin of the genus Homo. Interestingly enough, Professor Wood will be focusing more on what we do not know than what we know, and how we can draw conclusions from the incomplete fossil. So following Professor Wood's presentation, we'll hear from Professor Raymond, the Director of the Research Centre for Human Evolution at Griffith University, and is an accomplished paleoanthropologist with numerous nature papers and is a leading expert in in situ isotope analysis and important understanding. So Professor Grum will provide an overview of the new centre after Professor Wood's given his talk. So if you are tweeting this evening, it's all must be tweeting, I'm sure, please hashtag capital G, capital U, capital I, and a small case MPACT. It's all about social media, isn't it? So I'm now going to invite Dr. Michael Westaway from our newly established Centre for Human Evolution to say a few words about Professor Raymond DART, a renowned Australian paleoanthropologist, and we have named this evening's lecture in honour of Professor DART. Thank you very much.
Thank you very much, Nigel, for the introduction, and it's a great pleasure and somewhat of an honour that I get to talk a little bit about Professor Raymond DART. Now, he's very well known in paleoanthropological and archaeological circles, but very little is known about Professor DART outside of that sphere, which is a great misfortune, I believe. DART had very humble beginnings in Brisbane. He was one of 9 children and was born in, this is one of my favourite photographs of the 1893 flood. Here we see the West End Brewery being swamped, and they lost 600 hogshead of beer in that year that was washed out to sea. It was a tragic event, and it was also the event that saw the birth of Raymond DART. In 1893 he was born in Toowong and had to be evacuated with his mother out of their second floor level of the apartment, and they sought refuge in the Regatta Hotel just upstream on the second level of the Regatta Hotel. So there they waited for the flood waters to subside. And that was the beginning of Raymond DART in Brisbane. He later went on to Ipswich Grammar, studied at the University of Queensland, and went on to the University of Sydney and developed a stellar career. In the background of all this was occurring some significant discoveries in paleoanthropological research. At the time of DART's training and education, there were very few fossil hominids known in the world. There were Neanderthal, a couple of Neanderthal specimens, Java man, found by Eugene Dubois in the 1890s, and of course the Piltdown fossil, which was later reported to be a forgery. At that time, Dart was working in the 1920s. Dart was working at the University of Waterstrand as a lecturer and professor of anatomy, and was brought a fossil of the tongue child, and very quickly prepared the specimen and published it in the journal Nature. Now, this really rocked the British establishment of science, and here we have a famous painting, Grafton Elliott Smith, another Australian is in that picture as well, discussing the importance of the Piltdown forgery. And it was the Piltdown forgery really which was the emphasis for a lot of human evolutionary research, and also the specimens that were found across Eurasia. Africa was considered a significant backward. When Dart emerged with the Australopithecine, the tongue child, the palaeoanthropological establishment dismissed it largely as probably an ancestor of the chimpanzees, but not a human ancestor. They discredited Dart's discovery for many years, and it wasn't really until the 1940s, 1947, when Broome discovered Mrs. Plez, a more complete Australopithecine, that people began to look more seriously at the significance of Africa. But Dart played the crucial role in the 1920s of identifying that key important specimen. He was a student, I mentioned, at Ipswich Grammar, and we're very fortunate to have some science staff here tonight from Ipswich. But at the time, you know, he wasn't the most outstanding student. His report card suggested that his pass was satisfactory, and I think he's hardly right for university work. So there wasn't a huge expectation of him, but at the end of the day, he was triumphant and really established, I guess, Africa as the core of our understanding of human origins. And there is the tongue child. Dart lived a very long life. He passed away in the late 1980s. And I think it's a really important thing that we have this lecture series where we commemorate the significant Queensland, this man from Toowong in Ipswich. And it's with great honour that we have such a senior authority in palaeoanthropology here to present the very first Raymond Dart lecture. So please join with me and thank Bird before he even starts.
I want to thank you for your invitation. I also want to acknowledge that I'm in Australia as one of the Megunya Fellows of the University of Melbourne, so I want to make it clear that I'm very grateful to their support. These are a few pictures of Raymond Dart. On the right, he is holding the Taung skull, and on the left, he's holding the Taung skull. There is half a century separating the two pictures, and I was lucky enough to be at the meeting in 1975 when they celebrated the 50th anniversary of the discovery. And I met Raymond Dart, and he was extraordinarily kind. On the wall of my office, there is a reprint of the letter that he sent to Nature in 1925 that I rescued from a dumpster from a department of anatomy that was being modernized. So they threw out all what they conceived to be unnecessary material, and they said they had thrown out a lot of reprints. So I was an external examiner, and I spent my lunch hour rummaging through the dumpster and discovered this reprint, which has, with the author's compliments, with the compliments of the author. So it was a signed reprint of Raymond Dart of the Nature paper that people were throwing out because they thought it had nothing to do with molecular or cell biology. The notion of origins goes way back beyond Darwin, but what I want to talk about is the notion of origins in relation to the tree of life. And you can see in Darwin's the red notebook, which he wrote in 1835 on the right here, you can see that he sketches out this notion of a tree. And it's just impossible for me to look at that without the hairs standing up in the back of my neck, because he essentially realized that every living thing was related back to a common ancestor, much in the form of the tree here, you can see. And this is a three-dimensional tree sort of clearly, and I can only show it in 2 dimensions, but all the animals alive today are on the surface of the tree, and all the animals that have ever lived in the past are somewhere in the tree. But you have to realize that there are lots of branches in the tree that don't make it to the surface. So there are lots of creatures in the tree which are not ancestral to anything that's alive today, but they were ancestral to creatures which belong to branches of the tree that are now extinct. We like to think of ourselves at the top of the tree. I think it's more appropriate to put the politicians and the rest of us somewhere here. And modern humans are at the end of just one of the twigs of the tree of life. And when I was a student, I was taught this sort of dogma that modern humans are here, the orangs are here, the chimpanzees are here, and the gorillas are here. And the great apes are more closely related to each other than any of them is to modern humans. And the separation between the great apes and modern humans goes back a long way. And the separation was very profound. So profound that modern humans were put in one Linnaean family, the Hominidae, and the great apes were put in another, the Pongidae. So we were hominids, and the great apes were pongids. We now know, through various lines of evidence, through looking at molecules, this is a series of experiments done by Maurice Goodman, and you can see here he compares the albumin of chimps to the albumin of modern humans. And if there is a difference, there is a little white spur here. Okay, this is immunochemistry, which was largely developed by, or the notion of immunology was largely developed by an Australian. And you can see here, whereas there was when you compare the chimps to gorillas, there is a little spur. When you compare modern humans to chimps, there is no spur. So this analysis cannot discriminate between albumin, which is a protein in your blood. It cannot discriminate between the albumin of a chimp and your albumin. Whereas it can discriminate between the albumin of a gorilla and the albumin of a chimpanzee. Then, with the working out of the way that DNA records genetic information, and now using DNA to compare animals, it is quite clear that instead of the great apes all being more closely related to each other, it's now clear that the chimpanzees and bonobos are more closely related to modern humans than to any other great ape. And that we also have evidence of that from molecular data, not molecular, from morphological evidence. And this is a student of mine called Rui Diogo, and we looked at muscles in the head, neck, and the upper limb and the chest, and we just recorded their morphology, their nerve supply. And when you do that, you find that modern humans and chimps are more closely related on the basis of this muscle evidence than either is to gorillas. So now, we know, as much as we know anything in biology, that modern humans are more closely related to common chimpanzees and to bonobos than they are to gorillas or orangs. And we know that the common chimpanzee and the bonobo have probably been separate for a couple of million years, which is as long as the Congo River has been in existence, and the Congo River essentially isolates the range of the bonobos from the range of the common chimpanzees. So we also know from looking at the differences in DNA of those creatures plus monkeys and other things, it's possible to approximately calibrate the amount of DNA difference between modern humans and chimps and bonobos. And when you do that, it sort of comes out to about 6 million years worth of difference. And the difference is largely mutations which just occur like clockwork. They just happen. Especially in Australia, if you stand out under the sun too much, you get more mutations than some poor soul in Oslo where there is less sun. But if you just, but that's a trivial difference, but if you just, the amount of difference in the DNA between us and the chimps and bonobos is about 6 million years worth. So one of the origins questions would be, what is the origin of the twig of the tree of life that has modern humans at its end and no other living ape? And the answer to that question is about 6 million years. So what does this sort of twig of the tree of life look like? Well, it looks pretty complicated. So modern humans are here, the chimps aren't here, but these are all fossils which people claim are more closely related to modern humans than they are to chimps or bonobos or gorillas or orangutans. Now, you just have to take my word for it that some of those fossil taxa are probably ambitious. In other words, people they have recognized fossils based on differences which are not significant enough to suggest that they're dealing with a new species or a different species. But that's the topic of another talk. So one origin's problem is the origin of the human twig. Another one will be the origin of the genus Homo, because we are Homo sapiens. How far back in the past does Homo go? And then a third origin problem will be the origin of modern humans. How far back do people like us go? Now, we don't know the answer to that, but the fossil evidence would suggest that it goes back at least 200,000 years, and the DNA evidence suggests that it may go back to 300,000 years or so. So modern humans, roughly, folk like you and I, we're about 300,000 years old. That's not a very long history because the average mammalian species is about 1 million years, lasts for 1 million years. So we have 700,000 years to go before we are averagely successful. Okay. And if you think that it's a racing certainty that we are going to last 700,000 years, then you're clearly drinking or smoking something that I don't. And I think, we have to work very hard to make sure that we just get to the average length of a mammalian species. So what about the origin of the genus Homo? So what are we looking for? So we're looking for the origins of a genus. And to cut to the chase, most of my colleagues think that the genus Homo goes back to about 3 million years. I think they're wrong, and it probably only goes back to about a couple of million years, but why should you care? You care enough to come out this evening, but I will try and explain why I suggest that this is the more reasonable solution. So the questions I want to address are, what is a genus? Which species should be included in our own genus Homo? And when and where did Homo originate? Okay, so these are all origins problems. So what is a genus? Well, and then I put this slide in because I want to make sure that I acknowledge the contribution of Mark Collard, who is now distinguished in his own right, despite being my graduate student. And Andrew Dew, who is currently a graduate student, and David Patterson, who is currently a graduate student. So what is a genus? For a species to be included in a genus. So Mark and I worked on this, and we suggested that if you want to include a species in the genus, it should belong to the same monophyletic group or clade as the type species of that genus, and you're saying, why the hell did I come to this talk with this guy talking all this sort of gibberish? And so let me explain what a clade is. Okay. And I'm going to explain what a clade is. It's all of the taxa, no more and no less, that are descended from a recent common ancestor. You're saying, okay, it's still gibberish. It might be slightly less gibberish, but it's still gibberish. So let me explain what a clade is. This is there are lots of Toyota motor cars in this town. And if you look at the history of the Toyota motor car, the Toyota company made machines that made linens and things like that. They were a machinery manufacturer for weaving. And they decided in Japan that they ought to make their own motor cars. And so the Toyota company made its first passenger car in 1935, and in the same year it made its first commercial vehicle. So we know, because we know the history, that is the recent common ancestor of all Toyota motor cars. No matter what model, they're all descended, if they're a passenger car, from the A1, or if they're a commercial car, from the G1. We know that. So that's what a clade is. Okay. So a genus has to be a clade. It can't be a mixture of Toyota motor cars plus Land Rovers, or Toyota motor cars plus Fords. It's got to be limited to all the species which are descended from a recent common ancestor. So the other criterion we suggested is that the adaptive strategy of the species should be closer to the adaptive strategy of the type species of the genus in which it is included. This is gibberish. That is the type species than it is to the type species of any other genus. So it should not only be a clade, but the members of the genus should also be in the same grade. So basically, you shouldn't mix animals in the same genus that have markedly different diets, or animals that have markedly different locomotion, or animals that have markedly different skills, cognitive skills, or markedly different capacities of dexterity. You shouldn't mix things in the same genus. So it's a group of taxa that shares a suite of these adaptive features, and that's referred to as being in the same adaptive zone. Okay, back to the Toyota Motor Company. So the Willis Jeep, which was used in the Second World War and was made by the Willis Motor Company in America, was very successful. And so the Toyota Motor Company, they decided that they would make a four-wheel drive vehicle. They hadn't made one before. So in 1951, in response to the demand for a Jeep-type vehicle, they made something called the BJ. Strange, but they made the BJ, and here it is. So this is, within the Toyota clade, there is now a new grade of four-wheel drive cars. Okay. And so here, there are people who actually spend their time, sponsored by Bush taxes, making these things which they put on the internet. So you can see here is the original four-wheel drive. So that was then called a Land Cruiser. Then that begat the Land Cruiser station wagon, the Land Cruiser, and the Land Cruiser Prado. So in my mind, the four-wheel drive vehicles that are all descended from the B1, and they're all Toyotas, they would make a decent sort of genus, because they are a grade within a clade, and they're all more closely closely related to each other, and they are adaptively distinctive from ordinary Toyota passenger cars that are not four-wheel drive. So we're looking for both the grain and the clay. That's what we're looking for. But of course, this is all well and good when you know everything about this car, and you have, you know, photographs and you have designs and that sort of thing. But if the only thing you knew about this was, you know, a bit of a wing mirror and a bit of the body and about a quarter of the wheel and a bit of the front bumper and the, you know, a part of the radiator, then it's much more difficult reconstructing the history of the Toyota Motor Company. And it would be much more difficult to tell whether this was a four-wheel drive car or whether this was just a regular two-wheel drive passenger car. So what we're trying to do is rather more difficult because we're trying to do it with fragmentary remains without the benefit of this rich history of the Toyota Motor Company. So which species in our fossil inventory should belong to Homo? Now I'm going to move from a metaphor to do with motor cars to a metaphor to do with tennis clubs. Okay. I don't know whether you play tennis. I was pretty bad at playing tennis, but I did belong to a tennis club. If you run a tennis club, you presumably must have some criteria for the people that you're willing to accept into your club. Okay. When you start, you know, you're probably willing to accept almost anybody who's prepared to pay the fee. But then, you know, as you get better and the standard of the club improves, your criteria get rather better to find, and they probably get a little more exacting. So that's not a terrifically good metaphor for what I want to try and explain, but I want you to think of Homo as a tennis club. I want you to think, you know, it's a club. Who are you prepared to have in it? So this is a list of species, and the first species included in Homo was included by Carolus Linnaeus in 1758 in the 1758 edition of the Systema Naturae, and that's when he set up the notion of genera and species. And he said modern humans are wise, so we'll call them sapiens, that's our species name, and we will use Homo as the genus name. So that was the original member of the tennis club. Okay. Strict criteria, modern humans. Then, when Neanderthals were discovered, well, not when they were discovered, because they were discovered nearly 2 decades before 1864, and in some cases several decades before that, but nonetheless, somebody decided that even though Neanderthals did not look like modern humans, they looked sufficiently like modern humans that we could include them in the genus Homo. So this meant expanding the criteria for the tennis club to include people that have no chins, and people that have brow ridges and things like that. So then the next, not the next major one, I just want to highlight this because this Homo rhodesiensis was found just a few years before the discovery of the tall shark. And at that stage, Sir Arthur Smith Woodward decided that this cranium from Africa should also be included in the genus Homo, which meant relaxing the criteria for membership even more. And then, in 1944, Ernst Mayr suggested that the material from what used to be called Chukotien, which is now called Zeuglodian, which is also known as Peking man, that material, plus the material that's relevant to research that you guys are doing from Indonesia, that was included in the genus that was called Pithecanthropus, so Sinanthropus plus plus Pithecanthropus, Ernst Mayr decided, let's relax the criteria for membership of the Homo Club and let's include them, which meant including a bunch of crania that had much smaller endocranial volumes, much smaller brains. And so that was a relaxation. It made Homo even more inclusive. Then, so that's the situation at the beginning of 1964. So Homo included these taxa here. Then in 1964, Louis Leakey and Philip Tobias and John Napier, they decided that they wanted to make a case to include an even less modern human-like creature in the genus Homo. And this was Homo habilis. It had an even smaller brain. It had rather more primitive limb bones and so on and so forth. And here they are. This is Louis Leakey, and this is Philip Tobias, who succeeded Raymond Dart as the professor of anatomy at the University of the Witwatersrand. And Philip was a good sport, and he clearly wore the sweaters that his mother sent him. And John Napier, who was, he actually taught me primatology. He was a researcher. He was a professor in London at the Royal Free Hospital Medical School. And these guys made a case that this material from Olduvai Gorge should be put into a new species, and they call it Homo habilis because they thought it made the stone tools. So habile means habile. Okay, and they decided, perhaps even more controversially, to include it in the genus Homo. So, and then a little later, there was discovered some more fossils which were also included in the genus Homo, and these were fossils that I was involved in a minor way in their discovery and in a more major way in their analysis. So now I want to ask the question, how is this process of progressive inclusivity, relaxation of criteria, how has that affected the grade and the clade criteria? In other words, has this extension of membership, has it actually affected Homo? In other words, if you include Homo habilis, is it still a clade? And if you include Homo habilis in Homo, is it still a coherent grade? And this is something that Mark and I addressed in a paper in 1999, and we looked at a whole set of criteria, and we suggested that the H's stand for sort of Homo, and the A's stand for Australopithecus, and we suggested that either for some of these criteria, we either don't have the evidence, but for most of the criteria, the goodness of sort of Homo, the coherence of Homo as a clade in the grade works back to Homo erectus and Homo gaster, but once you include Homo habilis in it, then habilis made it more difficult to convince ourselves that Homo was a clade, and made it more difficult to convince ourselves that Homo was a coherent adaptive grade. And we can talk about the reasons for that afterwards if you like. So we argue that that you should probably put Homo habilis into Australopithecus and Homo rudolfensis into Australopithecus, and you should start Homo at the beginning of Homo erectus. Not a lot of people took any notice, but that doesn't mean we weren't right. So what has happened since that paper in 1999? How has the evidence since 1999, has it weakened our argument? Has it strengthened our argument. So since 1999, more fossil evidence has been found. Mead Leakey and Louise Leakey have been finding more fossils in northern Kenya on the eastern western shores of Lake Turkana. And they have found upper jaws and they have found lower jaws. And to cut a long story short, this new fossil evidence would in general, the new evidence hasn't changed the case that we were making about was Homo habilis, was it an obligate biped, how dexterous was Homo habilis, and so on and so forth. So there's been more fossil evidence, but you just have to take my word for it that it hasn't really weakened our argument that Homo habilis just wasn't up to snuff in terms of being an obligate biped, and being obvious, having wrist bones and having hand bones that were obviously adapted to make things like stone tools and so on. Quite elaborate stone tools. So as well as the new fossil evidence, there have also been some new data about the functional capacities that was so important for the argument made by Leakey, Tobias, and Napier. They interpreted Homo habilis as having a large enough brain that it was capable of sort of cognitive complexity. They interpreted Homo habilis as being capable of spoken language. They interpreted Homo habilis as being dexterous and so on and so forth. How reassessments of existing evidence how is that new evidence, how is it born on inferences about functional capacities? So since 1999, there has been new evidence about body size and shape that suggests that Homo habilis is much the limb proportions of Homo habilis and its body size are not much different than the Australopiths, which were probably its ancestors. Locomotion-wise, new interpretations of the morphology of the bones of the ankle have also suggested, and also the shoulder have also suggested that Homo habilis was still a climber. Okay. Now, if you're still climbing around, that's not, modern humans are obligate bipeds. Unless you're very young, you move around bipedally, or unless you indulge in self-poisoning. The only circumstance in which you see humans crawl around on the floor is either when they're very young or when they're very drunk. But otherwise, it makes sense to move around on your two hind limbs. It just doesn't make sense to do anything else. And we're not very good at climbing. Some of us are good at climbing, but in general, we're not very good at climbing. The evidence about cognition I want to talk about, and the evidence about diet I want to talk about. Life history is the rate that we go through the milestones in sort of maturity. And apes have a very short life history. Modern humans have a long life history. We take a long time to mature. Modern humans have a childhood. There is a period between infancy and adulthood when modern humans are still dependent and learning. If you look at apes, they go from being an infant to being a young adult. There is no equivalent in a chimpanzee or a bonobo or a gorilla or an orangutan of a childhood. So this slow life history of modern humans. That slow life history of modern humans, we now know, that evolved quite late. And what little we know about the life history of Homo habilis was that it was a quick, fast life history like that of the apes. So I just want to talk about cognition and diet. Now the cognition, there was a sort of a notion, here is age in millions of years, so this is the present, this is 3.5 million years ago, and this is cranial capacity. This is the amount of, brain and or the air that you have between your ears here. And the average modern human endocranial volume is about 1.5 liters. The average endocranial volume of a chimpanzee is about 350 cc's. So this was a very influential paper that suggested that for a long time, for about 1 million years, the australopiths, their endocranial volume did not really change very much. And not only for 1 million years, but also for more than 1 million years. And then with the introduction, with the appearance of Homo habilis, there was an increase. There was an increase in brain volume, and then there was another increase later on, and then brain volume. There was a period of stasis, and then there was another increase in brain volume at about 500,000 years ago. That led to this. This is an illustration from a textbook about neuroscience, suggesting that there was a burst of increase in endocranial volume at the time of appearance of Homo, which will be Homo habilis, and then there was another one later. So what we did was to look at the data, and this is a study which is just about to be submitted. There's much more data now than there was then. So here, there are many more data points, but those data points, and this is a bit about science, those data points, they're just points. They suggest there is no error in the measurement of the endocranial volume, and there is no error in the date. And that's probably unreasonable, because some of these estimates of endocranial volume are based on taking, a little bit of the right parietal and half the left parietal and extrapolating endocranial volume. There is a lot of error in doing something like that. And there is also error in how they are dated. So when you include the error, it looks like this. Now obviously, the likelihood of those points being, at the ends of each of those lines is less than the central tendency of them, but nonetheless the data look a lot messier than when you look at them just as point data. It's very tempting to plot things as point data because it looks much clearer, But of course, clarity and reality are often, they're often in conflict. So when you do this, and this is done by a bunch of graduate students who are much better at this than me, and they use lots of extremely fancy statistical methods to see whether these data were more consistent with stepwise changes, which is the hypothesis that I showed you, or more consistent with gradual evolution, more consistent with 2 stepwise changes or 3 stepwise changes, or stasis and a stepwise change, and so on and so forth. And basically, they looked at random walk, gradualism, stasis, and punctuated equilibrium, stasis and random walk, stasis and gradualism. When they did that not stasis, gradualism. I don't know why the hell I made stasis red. Gradualism is far more likely explanation for those data than the rapid periods of change, which is called punctuated equilibrium. So we now know that the evidence at the time of Homo habilis for an increase, a rapid increase in endocranial volume is not as good as people thought it was. So the other line of evidence is diet. And one way to look at diet is to look at stable isotopes, which are characteristic of the photosynthetic regimes of plants. basically you just have to take my word for it, that if there is a leaf in a shrub or a tree, then it's more likely to be at this end of the delta 13 spectrum. And if there is a blade of tropical grass, it's more likely to be this end of the delta 13 spectrum. The plants that are at this end are called C4, and the plants that are at this end are called C3. C4 are the photosynthetic process, which is characterized by the C4 signal. That is something that has evolved independently in plants something like 70 times. So it's clearly something that's highly evolvable to switch from the C3 photosynthesis to the C4, the chemistry, the photosynthesis. And you can see this is work of David Patterson. If you look at these isotopes in soils, and these are soils from the same series of fossil sites from where the Homo habilis and Homo agaster / Homo erectus fossils come from in northern Kenya. If you look at the soils, you see that there is no net change between just under 2 million years and 1.4 million years. It wavers around, but you just have to believe me, there's no significant trend. In other words, the soils don't change. But the animals do. So if I were to have plotted some chimpanzees on here, they would be in the C3 territory here. They would be here, as are the earliest hominin fossils, which are alleged to belong to the human twig. Then you move, and some early hominins here are very C4. But I want you just to look at these two red columns here. These are the earliest Homo fossils, which go from about 2.2 million years to 1.7 million years. And these are the later ones that go from 1.7 million years to 1.5 million years. Now, these are the Homo habilis ones, and these are the Homo agaster / Homo erectus ones. You would have thought that if Homo habilis is in the same adaptive grade as the earlier hominins, this is hardly a reason for saying that it's in a different, that you want to include it in the genus, because modern humans are, they're more likely to be up here than they are down here. So here you can see that Homo habilis, that its stable isotope signature is more like the Australopiths. Once you get to Homo erectus and Homo agaster, it's less like it. And what we think is happening is that by the time you get to Homo erectus and Homo agaster, you say, well, why does it have a grassy signal? Well, the answer is we think it was eating animals that ate grass. And if you look at the isotope signatures of the animals that are found, whose broken bones are found at archaeological sites, they tend to be more C4 than C3. So we think, so this is an argument for saying that there is not a break, there is not an adaptive break here at the beginning of Homo habilis, but there is one at the beginning of Homo erectus. And what's interesting is that if you look at all the other animals found at East Turkana, most of them don't change. They're like the soils. They don't shift. The only two that do shift, the only two apart from Homo that do shift, they actually shift in the opposite direction. They don't shift towards more C4 territory, they shift in the C3 direction. So Homo is the only taxon that undergoes, it's the only taxon that undergoes a significant enrichment in delta C3, delta carbon-13 values. So it's the only one that becomes more C4 through that time period. And this is a huge amount of work that David Patterson did, because each of these analyses, I mean, there are hundreds of bones, and each of them is very time-consuming. Okay, so when? So I've suggested this might be about 1.5 or something, or 7, 1.5 or 1.6 million years. So all these columns here, these columns, they represent what we call the first appearance date of this species and the last appearance date. And they are our current information about it. But I want to suggest to you that you will be a nutcase to take the bottoms of these columns and say, oh, that's when something started. Okay, let me explain why. Because each column represents a hypothesis about the existence of a taxon, and it represents a hypothesis about the ages. But they are observed first and last appearance date. They are not the actual first and last appearance date. And so what I've done here, you and I know that all these circles, despite being slightly different shades and different sizes, they all belong to a single species. Okay? You and I know that. But the person who goes out to look for fossil evidence of that species doesn't know this. They just get a site sample here, and the oldest fossils from their site, they correspond to this time, and the youngest ones, they correspond to this time. So although you and I know what the actual first appearance and the last appearance date is, these people only know what they know, okay, from the only sample they have. So the observed first appearance date is much later than the actual one, and the observed last appearance date is earlier than the actual one. And then you go and find another site, okay, and you move your first appearance date, you say, oh, much older than the previous one. You move your first appearance date, it's still the observed first appearance date. It's not the actual first appearance date. So what the columns are not are statements that you can really take to the bank about the timing of the origin and extinction of taxa. So if you start saying, oh, let's look at the changing climate that corresponds to the bottom of the Homo erectus thing, that's an explanation for the appearance of Homo erectus, you're crazy. Okay? Because you're just chasing a sampling artifact. Okay? You're just chasing a sampling artifact. So where? Well, I've suggested to you that the fossils from around Lake Turkana and Olduvai belong to Homo habilis. Oh, that's where Homo arose. Well, remember, and then you look at all the sites where early hominins have been found in Africa, and you're reminded of the fact that the drunk looks for her keys under the lamppost, because that's the only place where you can see. It's not where the keys were dropped. Okay. So this is where we can find evidence of early hominins. But the argument about range is the same as the argument about the timing. You and I both know that this species extends across a range which is about the same as Western Australia and the Northern Territory. It's a big range. Okay, you and I know what its range is. The scientists, they don't. The only way they can get an estimate of its range is by finding fossil evidence. Because if you find fossils in a site, you know it's there. But if you don't find fossils somewhere else, you can't be sure it wasn't there unless you find so many fossils that you can be absolutely sure that if a hominin was there, you would have found it. Okay? So it's sort of difficult. So, here's our site A, and so we have a range, the observed range and the actual range. Here is our site B, it changes the observed range a little bit. Here is site C, it changes the observed range a little bit, but it's still much, much less than the actual range. So if you think that by looking at 3.5% approximately, generously, of the surface area of Africa is likely to have recovered comprehensive history of human evolution, well, I can't believe that you would buy that. Okay. But that's the reality. Okay. So it's highly unlikely that we know everything there is to know about human evolution in Africa. So given that we cannot know what data are missing, this is the Donald Rumsfeld School of Philosophy. There are known unknowns and there are unknown unknowns. Okay, but given we don't know what data we are missing, what should we say about the origin of Homo? And the answer is not much. So the answer is not much. I think it's probably more, Homo is probably more likely, but the first evidence of Homo erectus homogasca is about 1.7 million years. Only God in her infinite wisdom knows exactly when Homo appeared. Okay. And I have not been smart enough, or I haven't done the right things to be able to talk to her and say, just tell me. Do me a favor and tell me. But no, I haven't got that yet. So I want to thank you for your invitation. I want to say what a privilege it was to give this as the first of the series of Raymond Dart lectures. There is another series of Raymond Dart lectures at the University of the Witwatersrand, and I was privileged to give one of those Raymond Dart lectures. So there are two places in the world that will recognize the contribution of Raymond Dart. I was lucky enough to meet him. I was lucky enough to know people who worked in the department when he was the professor. And they were united in their view that he was just the most lovely man to work for. He would come into work in the morning, he would stop at each person's office, find out how they were, ask about their family, and by and large, people would have walked on hot coals for Raymond Dart. And so not only was he a very extraordinary scientist, he was also an extraordinary human being. Those two things don't always happen. So thank you very much.